Hi, I'm Andrey Petrov. I'm Shazo on the internet. If you've heard of urlib3 or you've ever used this language, you've probably used some of my work. I do a bunch of open source stuff. I do this other project called SSH Chat, which is written in Go. It's kind of cool, but nothing to do with this. And so I'm going to talk about running Go inside of Python and Python inside of Go. But a lot of these ideas you can apply to any other languages as well. And so even if you're not interested about Go specifically, hang in there and you'll probably learn something. So first of all, do any of you already use Go or tried Go or like Go? All right, so a handful, maybe a dozen. Cool. For the rest of you who haven't really heard much of Go, I'm going to give you a super quick intro about the things that I like about Go. The syntax is really simple. In fact, I would argue it's one of the simpler ones to learn. There aren't a lot of features in the language. There's no classes. There's only one kind of loop. It does have some cool concurrency features, but those are very much optional. It builds really fast, so it almost feels like you're using an interpreted language. Usually the smaller projects build in milliseconds, and the larger ones, if you cache it as it builds really, really fast. So you can iterate really quickly and see your result as you go. It's statically typed, so if you're expecting an integer and you pass in a string, you'll get the errors before you even run it. A lot of the time, we write a lot of unit tests to make up for the reality that up until recently, we didn't have static typing in our language. And this kind of alleviates a lot of that work. The way you deploy it is a statically linked binary, so you don't have to worry about dependencies. You don't have to worry about having Python 2 versus Python 3 versus whatever feature is missing. You just build it into a binary and ship it off to a server and run it, and it's fairly straightforward. Yes? Oh, please. Yeah. No worries. Sorry for the little intermission. Hello. Okay, there we go. Getting myself. Cool. Or can you speak to that? It builds to every platform. So one of the benefits of interpreted languages usually there's interpreters on different platforms, and you can run on all those platforms. Whereas Go is statically built, but they have targets for pretty much every platform you can think of. There, you can build it from Mac into Windows, from Mac to Windows, or like Windows to Linux, or you can build it for Raspberry Pi, or whatever you want. Concurrency is a native aspect of the language. You just put Go in front of a statement, and that makes it run in a separate kind of thread pool. And the standard library is really, really good. I know that Python is known for having batteries included, but sometimes our batteries are a little rusty, and some of them are like directly rewritten from a Java version, so they're all really weird. Whereas the Go one, it's kind of a clean slate. They didn't translate anything from other libraries. Like they don't expose the underlying C APIs very much. Whereas here, if we import socket, for example, it's just literally the C API, which is most people don't really like very much. And there's gophers if you're into that. So that's where you look for them. So this is a cool little drawing. So the idea is we're gonna see how we can, if for example you already have a code base in Python and you want to run some Go, like for example, say you have two different teams, and your main app, web app, is in Python, but then you have some like backend stuff in Go, and you want to like run your Go from your web app for some reason. This is going to be like a brief introduction for how to do that. So Go in Python. This is the easy way to do it, nice and simple, and we just exec the Go from inside of Python, and we're done. That's it. Cool. Thank you. No, it's joking. But no, this is actually a thing that, I mean, not quite like this, but running two separate, like a Python process and a Go process and having them speak over sockets or whatever is actually a thing that a lot of people do, and that's totally legit. But we're going to do something more interesting. So Python speaks with C. A lot of us know this because a lot of the libraries that we're using are built in C. So when you pip install and you see a bunch of output that's building stuff, that's probably C. So stuff like LXML or PIL and all those C bindings. So Python clearly speaks with C. And Go speaks with C. I'll show you what that looks like. It's actually even easier than in Python. So by the transitive property, we should be able to make Go speak with Python, right, through C. And that's what we're going to try to do. So before we dive into that, we need to keep in mind that we're going to run into some challenges along the way. So both Python and Go have their own runtimes, and that includes the GC, the global interpreter lock. If you're using PyPy, you have a just-in-time compiler which can rearrange what's being executed on the fly. You have resource pools. So there's also kind of things that both sides have that we need to worry about how they interact with each other. And then the other thing is the two languages have very different features and ideas, and they don't necessarily translate one-to-one. So in Go, we have interfaces and channels and Go routines, whereas those ideas don't really make sense in Python as much. And in Python, we have classes and generators, which don't make sense in Go. So we're going to have to come up with some way to translate those ideas from one end to the other while still working. And then there's a bunch of other language constructs that we'll have to worry about. So this is kind of what that looks like. We have the Go runtime on the left and the Python runtime on the right. And then this all kind of lives in this C barren wasteland of overflows and memory leaks and dragons. And we're going to traverse this wasteland from one end to the other and make them speak to each other while all running in the same process. So in this particular example, so you can build anything, but we're going to build a web server. So to kind of get you an idea of what that's going to look like, so this is what a web server looks like in Go. This is a very basic web server. We have the name of the namespace at the top, main. We have a few imports. And then if you look in the main function, we assign a handler for /, which is like the index route, to this index method. And then we listen on port 5000. So pretty straightforward. And then the index receives two variables. It has a response writer, which is an interface. So basically, that's the thing that we write into in order to render a response. And then it has the request information. That's a structure that has things like the URL that was requested, the referrer, the IP address, all those kinds of things. And then similarly in Python, this is what a web server would look like. So using something like Flask, we create an instance of it. We register a route for /, so we have an index callback. And then Flask uses an API that returns the thing we want to render. So we just return a string hello world. And we, if name is main, we run it on port 5000. So it's a similar thing. Now imagine if we could do this. So this is written in Python, but we import this module called GoHTTP. And we, similarly to the previous one, we create this handler for index. It looks a little more like Go, so it takes two variables, the writer and the request information, and we bind it. So this is kind of the before and after. This is the Flask version versus the kind of Go hybrid version. And honestly, the Go hybrid version can look like whatever you want. I just kind of wanted to make them look somewhat similar, but also not too similar, so not to throw you off. And because it's kind of the meat of what we're dealing with. So we have these handlers. The Go one is on top. So we have a response writer and a request. And the hybrid one is in the middle, where it takes a response writer and a request and calls .write instead of using any helper. And then the Flask one is at the bottom. So it's kind of a gradient from Go to here. But this is actually a real thing. So this is a library I wrote. It was an R&D project that Glider Labs needed help for. They wanted to see if they can write some library code in Go, and there was a new version in Go. In the new version of Go, there was a feature where you can build it as a shared library. And they want to see if we can use it to make a Python library. So we built this out, and it's actually a working thing. Try it out later. And I'm going to talk about how it works underneath. So if you ever want to build something like this yourself, you kind of know the high-level mechanics of it and what to worry about and what the steps are. So the plan is this. We're going to write some Go code and export it into C. And then we're going to write some scary C that hopefully you don't have to worry about too much. And then we're going to wrap it in something that looks more Pythonic. And then we're going to instrument it a little bit to make it work. So these are the steps that are coming up. So first of all, the world of Go. In Go, this is how you call C from Go. So Go has this built-in thing. If you import C, that's like this. It's this magic module that doesn't actually exist, and it enables some things in Go. And you can write in a comment, you can write C code right above it. And when you build Go, you just do the normal Go build stuff. It knows how to inline that C code and link against it and set it up. And it's kind of cool. You can see in our main function, we're calling C.theAnswer, but the answer is defined in a comment right above it as literal C code. And we can call one or the other and run it, and it's fine. And now, on the other hand, if we want to call Go from C, it's also really easy. Again, we import the C namespace, which gives you these extra features. And then in a comment, you write export and then the name of the thing, of the name of how you want it exported. And then we have a function here that returns a C integer. So note that I'm returning C integers rather than normal integers. You can actually do normal integers as well, and Go will figure out what you meant. But just so you know exactly what's being inputted and returned, so there aren't any surprises, I recommend using, for any function that's going to be exported as C, make sure you're using C types for input and the output, just to make it more obvious what's going to happen. And then we build it as a shared library. So this is a new feature in Go from like a year ago, where you can build it as a C shared library, and that outputs a shared object, so libanswer.so. And then and that also exports a header file. It generates a header file for us, and that tells, when we include it in our C, it tells it how to read it, like what the symbol names are, what the different types are, and we can directly use it. So I'm calling the answer, which was defined in Go, and I'm calling it from a C binary, and then I build it, and it links, and everything works. Now that we know how to do Python, and then we know the Go and C, we're going to do the other side. So Python, there's a couple ways to do C in Python. So there's C Python extension interfaces, which comes the default built-in thing. If you've ever seen a bunch of PyObject stuff littered all over a bunch of C code, that's what it's using. And it's a little lower level. It doesn't do as much for you. You have to define a lot of boilerplate, but it doesn't need to install anything additional to it, and it gives you access to all of the interpreter stuff, so you can lock the GIL, we can release resources, all that stuff. But then there's another thing called CFFI, which is a wrapper, and it generates a bunch of code for us. And that ends up looking a lot more like the Go version, so it's really simple. So in these examples, I'm going to use CFFI. And this is what CFFI looks like. So you pip install CFFI, it does its thing. Then you make this build Python script. You define an FFI context. You define the header. So this is what our function is going to look like. It's going to return an integer. It's called the answer. And then we define the source of it. So similar to Go, we can do it in line, or we can reference an external library to include in there, or whatever it would work. So here we've defined the answer, returns 42. And then we build it, and that generates a bunch of things for us. It generates a C code, generates an object file, generates a shared object file. And then similarly, we can write a Python module. So by default, it creates a namespace lib inside of the module. We import lib from it, and then we can kind of use it directly, or in the future, we're going to be writing a wrapper around it to kind of hide the C aspects of it to make it look more normal. So that's what CFFI looks like. And on the other hand, one more thing we're going to need to do, because we're registering a handler from Python that will go to C and that will go into Go, we're going to need to have this. So this is how you make a callback that will be exported into C. And there's a little more instrumentation that needs to be done. The documentation is available here. It's just a few extra lines that look scary that I didn't want to include in here. But you can ultimately, we end up with a header that looks like that. So it's an integer with a function named add that is a reference, and it takes two integers. So remember, we have all these barriers, and then we need to figure out how to work around them. So we know how to run Go from C and C from Go, and Python from C and C from Python. So we could already start interfacing with them. But
if we're not careful, we're going to get segmentation faults and overflows, and things are going to deadlock, and things are going to crash. And this is basically what you have to worry about when you're dealing with these things. So first thing, when you're doing this, is never share memory. And specifically, because both of these runtimes have their own GCs, and that means that when you allocate a variable on one side, it can get moved around or it can get removed if it's not being used anymore. So if you allocate a variable and you use it from C and you use it into Go, and it gets moved and Go's still using it, it's going to crash because it's not going to be there anymore. It's going to access an invalid memory address and it's going to explode. So we want to avoid sharing memory from one runtime to another. And recall that for our handler that we register, we're basically going to have to send in a bunch of information. So specifically, we're going to have to send in the request, which has a bunch of information. So what we're going to do is we're going to write this wrapper in C that includes all the information that we want. So it has a string that has a method, it has a string that has the host, and we're going to copy it over into C land. And we're going to basically make a copy of it and pass it on. So if Go gets rid of it, it doesn't matter because C has its own version of it. And if C gets rid of it or anything beyond C that we pass it into, it doesn't matter because Go doesn't deal with that variable. It has its own copy of it. So second part, once we're done copying all the things we want to pass in, we want to translate these ideas. So specifically, here we need to pass in an interface across. But Go has interfaces, but Python doesn't have interfaces, doesn't know what an interface is. So we need to write, this is what in Go this interface looks like. So the response writer has two things that we really care about, has a bunch of other things. So it has a write method on it that accepts some bytes and returns a number of things that were written, and then it has a write header, which basically returns which sets the status of the response. So it's a 200 or a 404, whatever. So basically, we're going to have to write C that abstracts this stuff. And we can do it in Go. So Go has the export stuff. So we write these wrappers in Go that gets exported into C. And we can use all of the Go ideas, like interfaces, inside of this Go bit. But once it gets exported into C, we kind of lose all of the access to that. So this is a little scary looking because there's a lot of referencing and dereferencing. I have like a slightly simplified version. But the idea is for response writer write, all we do is we take a reference to the writer and what we want to write, and the number of things we're expecting to write to avoid overflows. And then we convert it, and then we convert it to the interface inside of Goland, and then once we're done, we just return the integers. So anything coming in and coming out doesn't need to know anything about Go, but the Go stuff can stay on the inside. And then similarly, once we get over to the other side, we open it with CFFI, and we get access to these same interfaces that we just wrote. So we have lib.responseWriter inside of write over there. And that's where we're accessing the thing, that wrapper we just wrote. And again, we can add another wrapper on top of it to make it look more normal. So it doesn't look like it's C hidden inside of Python. It just looks like normal. And overall, this is kind of what that transition looks like. I really like this evolution here. It starts from Go. This is the interface we have that we're dealing with. And then we export it into C. And then we get a header like this in C. And then from C, we get this from CFFI. And we wrap it. So it starts looking like native Go, and it ends up looking like native Python. And everyone's happy, right? But then the last thing is, if you know what interfaces are, they're actually pointers that have some extra information on them that basically you know what methods are on them. And we can't share memory, right? So in order to make this work, we have to pass in a response writer from Go into C into Python into C into Go. And we can't do that. So the trick is we use something called a pointer proxy. I don't know if this actually has a name, but it's something that everyone kind of runs into. It's like, wait, I have to go across runtimes, and I can't share memory, but I have to send a reference in all the way through and back. What do I do? And this is kind of the solution that everyone seems to have landed on. I'm not sure there's another solution that works. But this is what it looks like. It's actually really simple. It's basically what you'd expect. It's like writing your own little memory management that's really dumb. All it does is you take any kind of object, you call reference on it, and that returns an integer. And then you can use that integer however you want. And then later when you want to dereference it, you just give that integer back and it returns the original object. And then you can also free it once you're not using it anymore. So this is the implementation in Go. I stripped out the actual bits, but it's just each one is 2 or 3 lines. So it's basically exactly what you'd expect. We have a counter. Every time we add one, we increment the counter. And we have a map, so it's a lookup from the integer to the object. And then when we get a new object, we increment the counter. We stick it in the map. We return it. And then later we remove it from the map. Super simple and super useful. And the way we use this is like this. So we create a pointer proxy. Every time we want to send in the interface, we reference it through a thing that gives us an integer. Then we send it into C that does something with that integer that we don't care about. Then later, we get that integer back, and we can look it up and get the original object and do something with it. And that makes it safe to send references to memory. It's like memory of memory, almost, without actually sending the actual memory in and worrying about it getting thrown away and moved around. OK, so because we can speak to C from both sides, they can speak to each other, so that's what we learned. We do need to be careful of runtimes, because things can change, they can disappear, they can move around, they can get optimized. We need to be extra careful with sharing memory. Sometimes we share memory without even realizing. And we need to create either copies of it or create indirections of it where we manage our own memory of references to it. And finally, we have to come up with translations between different layers. It's like, imagine if there's some kind of poetry that rhymes, and we use in one language, we want to translate to another language. You can't just use Google to translate it, because it'll lose all of the rhyming. So a translator would need to work extra hard to kind of express the spirit of the underlying thing, as well as what its meaning. And that's kind of what we have to do here. We have to figure out how to translate ideas of one language into ideas that map onto the other language, or ideally ones that aren't reliant to it by doing something that C understands. And then other things to worry about. So because we're dealing with C, unless you're really experienced with C, we're going to deal with memory leaks. So make sure every time you allocate a string or any bytes, any kind of like non-elementary thing like integers, you need to free it. So in my examples here, I don't specifically free it. So here's just to make it simpler. Every time you see this, assume there's a free somewhere at the end. You're going to have races, because there's the GIL. So if you're accessing a resource from C that is also being accessed through another runtime, and they're both locking the GIL, you're going to get into deadlocks or races that you have to worry about. If every time you go from one language to another, there's a jump, there's a leap. It has to put a bunch of things in the stack and switch what it's talking about. So there's a constant overhead every time. So don't put these kinds of things in a hot loop. Ideally, put the hot loop in where you want to end up rather than on the outside. And that overhead is not huge, but when you're doing it millions and millions of times, it does add up. And finally, I'm sure all of you know that writing C code is scary and hard, and rightfully so, because it's really easy to essentially hurt yourself doing it by having all these buffer overflows and security issues, and people are going to hack into your code and steal your Bitcoins or whatever you have on your servers. And finally, it does add a lot of indirection. So you need to remember, we have these layers that we have to translate from native to native. And unless you're careful sealing it in a way that doesn't interfere with things, you're going to get a mess all over the place. And just to kind of wrap up, I want to do some benchmarks that don't mean anything. Just kind of a very simple hello world, so it's very contrived, and obviously don't take too much meaning from this, but that kind of gives you the idea of how this does. So I have the original Go version on the left, and then Go to C, and then Go to C to Python, which is what we saw here. And then you have GUnicorn with Flask, and then Workcircle with Flask, which doesn't have any concurrency. And you can kind of see there's substantial differences. This original Go version handles 9,000 requests per second, and the slow Flask version handles 600 something requests per second. So it's pretty substantial. But again, this is on my laptop, and it's not very serious. It's a very simple example. And that kind of gives you the idea of what the upsides can be. And that's it. That's our little journey from going to Python. Thank you.
think we have a little bit of time for questions. So if anybody has a question, please shout it out or step down. Set up the mic right here. Any questions?
No?
Anybody?
Cool. Yes, over there. Shout it out.
Are there any existing Go libraries that I would want to use in my Python?
Are there any good Go libraries that you would want to use in your Python? So I mean, a lot of backend kind of networking stuff is being rewritten in Go. Like every new database or infrastructure like Docker and things like that, they're all written in Go. So if you want a kind of deep integration into these infrastructure devices, you can do that. But in terms of like just using Go because you like some library, it's probably not worth it. Just from all of the risks and all of the overhead of writing this. It's just if you have a very substantial piece that you would otherwise not be able to use, I think it would be worth it. Anyone else? Yes.
I was confused about why you had to implement a C struct for the HTTP request object.
Yes.
And does that imply everything gets copied twice? Or is everything copied once?
Copied once. So basically, we don't want to pass in the original Go struct because that'll be sharing memory, right? So we make a C struct, and because C doesn't have its own runtime that'll mess with our memory, we copy it into C, and then it'll stay there. And then we pass it into Python, and that we use it there, and then afterwards we can free it. So it gets copied once. Anyone else? Yes. Sorry for the screensaver.
Could you tell us a little bit about error handling? Because it seems like that would be very incompatible.
I mean, it's the same idea as you would, like, we have to translate the ideas of exceptions and errors. So in Go, errors are just values that you return. So if you want to handle an error from Go into Python, you either have to translate something that C understands, which is also going to be like the number -3 or something like that, or some kind of constant. So the same idea you would handle any other value. Whereas exceptions, you would have to kind of wrap them. So you have to intercept them and change them into some value and send them through and back. So everything you'd have to do manually. So there's no kind of magic you can get exceptions in Go all of a sudden and back. Anyone else? Cool. So this, you can check it out on GitHub. You can build it. You can run it. You can play with it. It only implements a small subset of the API. If you want to add more, feel free. I also wrote up much of this on the Heroku blog. That's the URL if you want to reread it and like recap. And also I tweet a bunch. And if you want to see some of my other stuff, that's my homepage. Thank you.